Everybody to our March 1st event with Eric, and this is his fourth time to join our event as a speaker. And let's start it.
Thank you, Helen. My thanks to Helen Ma. Well, this I expect to be an open mic kind of session. If there's anyone who has questions or comments along the way, you can speak up, tell me to do something different, whatever. This is about the experiment mostly. I'm going to demonstrate, and my intention is to show you some gamma ray spectroscopy in a way where you can believe what the experiment is saying and how it works. So I'm going to switch to the LaCroix oscilloscope. Now it's running. It's been running for let's say what is it? You can see it's 10 kiloseconds here, the duration, and we have 774 pulses in the region of interest. There's going to be much stuff that I'll have to go back to have you understand because I have to start the experiment. It takes about a half hour for the experiment to run nicely. So I'm going to erase what I have on the screen, which has been running, and I'm gonna start it normal. It is. I'm going to go to change the trigger level to just uh, the uh, the detector in the back, and I want to show that there's a spectrum that is revealed. So there's everything at once gets to be revealed on this great oscilloscope. So right now we're looking at the pulse height spectrum, this orange, of the second detector. There's two detectors. The first detector is up here, the second one, and we get to see the pulses and the actual pulses of each detector. We get to see the spectrum of each detector. And there's also these timing pulses, this square thing here. So, but right now I'm just looking at one detector because I triggered it on that. And I want to point out that uh, there, I actually prefer not to change the setting on it. So I'm going to switch to my other camera and we'll look at a pulse height analyzer to see like, well, what are these gamma rays? so this is a better instrument for looking at the pulse heights where I just showed on the LaCroix, but this is a better instrument for seeing it. And this is showing it in logarithmic mode. I'm going to put it on linear. So there's this great big peak, and it's called the photo peak, where the gamma ray detector energy is showing up. And so what it's about is that there's actually a lower energy, a smaller pulse of an X-ray. So if I was to change the lower level, I would bring in this other. I'm going to start it over here so you could see. Erase. And so there's an X-ray that. So the point of doing this is to understand we don't capture the X-ray. The X-ray is emitted in coincidence with the gamma ray, and we want to show coincidences between gamma rays from two separate detectors, but we want the gamma ray to come from one source. We're going to start with one at a time gamma rays to get going to two detectors. That's what the experiment is. And so anyway, I'm just showing that so I'm going to turn the knob and do erase again. And let's see, let me put it on logarithmic. So I'm showing that we do a pulse height filter to eliminate the X-ray. And so that's what's going on in the LaCroix oscilloscope as well. Uh, so now let's go back to the LaCroix oscilloscope, and and I'm also going to change the camera and just look at a few other things. And so now I'm gonna change the trigger system to the smart trigger, and erase, clear the sweeps, and well, I could show the first detector too. Let me do that just for completeness, to show that, like, I was looking at the second detector before. Now I'm looking at the first detector. What's important to see also is that the pulses are well behaved. They're not overlapping in any nutty way to make misshapen pulses where people can see, well, what's going on with that. So anyway, this is the pulse height spectrum, the actual pulses. The timing pulse is hidden in there. And I'm going to show the schematic later, but I want to get this going first because it takes about a half an hour to see this experiment run well. So I'm going to put it on smart and clear, and that should get it started. We'll see if it does anything now. You know, every minute or a few a minute, there's going to be pulses, and they build up. So there's one. Good. So it's working. It'll take time. So now, I'm going to do some other things while this is going in the background. Let's go to my camera again, where I'm going to look at the actual experiment. Let's zoom in on what do we actually have here. So it's inside this chamber of lead that I built. This incredible chamber of it's a cylinder about a foot diameter, and if I zoom in, so it's going to be hard to really make out what's going on. I have a separate picture of it. Anyway, I'll bring the camera way in to see if you can tell what's going on here. There's this yellow part is the radioisotope. It's 50 microcuries of cobalt 57, and behind is two detectors. Let's see if I can get a view from the side for people to see that. I don't know what you're seeing. I'd like to hear if you see that. Okay, good. So I'm going to point out in another graphic, which is the small detector and, and the big detector. All right, now let's go to the light. I have these detectors at hand to point out pretty directly. So this is a half-inch diameter to get a good background. It's hard to get a background. The half-inch diameter detector, and the gamma rays are going to go through the foil of this. It's a thin foil to a scintillator. The gamma rays go through this. The idea is that half of the gamma rays. Well, what's a gamma ray? We're going to find out what a gamma ray is. But radiation goes through it and then to a larger detector like this one. Uh, what I have installed in the experiment is something a bit bigger. This is a 2-inch diameter detector, uh, gamma ray detector. And so, all right, let me set this camera down on its tripod. And I'm going to aim this at the more at the numbers. So the numbers, we're gonna use these numbers for of the counters for seeing the singles rates. So uh, let me reset. There we go. So those are the pulses that are coming in from the gamma ray detectors. And we do see the pulses on this oscilloscope, like I showed before. But anyway, you get an idea what the rate is.
Eric, is the
Yeah.
second one on the right the second detector?
Correct. Yes. Good. Yeah. So the first detector has a higher count rate. It's closer, and the gammas have to go through that. And then to the second detector, a lower count rate. Now, in the past, I did this experiment with a thinner detector, this one, and it worked better. Oh, they can't see that. You can't see that. Okay. Uh, this is like a 2-inch across. I keep switching between inches and millimeters. This is specified to be 4 millimeters thick, but it broke. I can't use it anymore. So, but in the past, I had some of my best data from this detector for the gamma rays to go through it, but still pick it up. So the detector forms a dual purpose. It's like a combination between the beam splitter and a detector. And I've done experiments where they really were beam splitters, slabs of different materials in front of the detectors. So I've done it both ways, but this works really well where where there's a thinner detector, but it broke.
So Eric, can I just clarify the current setup is a scintillator with a photomultiplier tube, and we're looking at the counts.
Correct. All right, let me go back to the slides. I have that. Right. So, right, the gamma goes to a scintillator. The scintillator makes a tiny flash of visible light, and then a photomultiplier picks it up. And so these are spectra I took way long ago. In this, in that Tracor spectrum analyzer that I had connected through the serial port to program it. This is logarithmic on the vertical. And so these peaks are really gigantic, but I'm just showing it logarithmic. So there's the X-ray, there's some Compton shifted rays, there's the gamma ray proper. All right, so this is cadmium 109 and cobalt 57. Cobalt 57 is what we have here. Further up in the spectrum, there are these pileups where two of them that superimpose in the scintillator can make big pulses. And there are a few different mechanisms for making these pileups, one of which I claim to be my unquantum effect. Uh, so let's see, next slide. Yeah, this is a schematic of what I have going. So there's the isotope, the thin detector, the thick detector. It's the isotope is in a lead collimator to guide the rays such that the rays have to go through the small detector to get to the big detector. Okay. And it's touchy how to adjust this. This is a pulsar system where I can inject a signal into both channels to align the timing. And I could do that maybe at the end if you ask me to. So these amplifiers are the nuclear instrumentation in that rack of equipment I showed earlier. and these pulse height filters, also called single channel analyzers, they're the nuclear instrumentation NIM. It's in the NIM rack. So, and these are set to let through the pulse heights that are characteristic of the gamma ray that we're examining. And so here I tap off, and I have my pulse height analyzers, the other instrument that I showed. And so there's 4 signals going to the LaCroix oscilloscope. The analog pulses that are then analyzed, go through the pulse height filters, and then the digital. The pulse height filters is about taking the timing, to pick off the timing. When does this pulse happen? And then it creates a square wave that goes into the digital oscilloscope. And then we do a timing analysis from these square waves. So, all right, this is a nice picture from the side as to what I have put together with the radioisotope and the small detector. And the big detector is, there's extra lead around it for shielding, and is a sort of a slot in front to just let through, so it doesn't get anything from the side. So it has to pass through the small one to get to the big one. Now, what I have here is from a few days ago, a really good version of the experiment. And so we're going to see this again in a few minutes, what's actually happening. But what I want to point out from this experiment is that over to the side where I boxed it off, I did a count of how many are in I call the wings of the histogram on the side. I call it the wings. So if you do a count of the rate in the wing, that should equal accidental chance. Like if there was no peak here, if it was just noise that we're seeing, like from background or from a test. Well, everybody else has just seen noise in this experiment. I'm the only one to see a peak where you're looking to see, well, is there a mechanism that does greater than chance? So I'm going to show other people's experiments and the history of how people have looked at this kind of time histogram. But since it's here, I want to point out that there's a simple calculation. This is the calculation you do for chance, where, no, it's here. The rate of chance is, you take the rate of the first detector times the rate of the second detector, like I was showing those numbers on the NIMBIN. That's where they come from. And then there's this time term, and that's the width of time, the spread of time for which you're counting. So in this case, it was 100 nanoseconds. And so that's what's here on the oscilloscope, and also here where we're measuring how many happen in the peak. So there's this tau, this time constant term that's used. Excuse me. That's so there's only one equation, pretty much one equation that's used in this whole analysis, which is the chance equation I'm showing here. And so you multiply all this out, you get a chance rate. Then you compare. In this case, I'm showing that the chance rate from the calculation, from reading the rates from the singles rates, reading the singles rates and this time constant, you multiply it out, you get the chance rate. Then I'm showing, well, you look at the wings and it's the same number. So this is a test of the chance equation to show that it's for real and why and how it works. And so the wings are about reading chance. And so that worked out nicely. Let's see, how is the LaCroix doing? Let's just take a quick look at that. Oh boy, there's a nice peak showing up. I like that. I may want to widen it. Let's
Eric,
see.
just if I could ask you to, in that oscilloscope, the white histogram is the time difference
Correct.
histogram? Okay.
Good. Good. That's right. Trace C here. The white, the big white is the time difference histogram. And that's the most important part of the experiment. Good. So let's go back to the slides. So there are certain criteria that I discovered that have to be met in order to make this experiment work properly, to make it do better than accidental chance, to defy quantum mechanics. There has to be isotopes that emit only one gamma ray per decay. There's a whole test for that I'm going to get to. I'll show you. It has to decay to where it only has one stable isotope after it decays. It has to decay to stable. Then it has to have a reasonable half-life to work with. Like some of these things last only a second. Different isotopes. So for what I was able to purchase are these two isotopes, cadmium-109 and cobalt-57. And so this is the graph of the absorption of our sodium iodide detector versus the electromagnetic frequency on the horizontal, which is also the pulse height on the horizontal, proportional to the pulse height, and also the electron volts energy of detection. That's all three things are what the horizontal is about. So there are different mechanisms in the detector, the way it responds. There's this photoelectric effect response curve, and there's the Compton effect response curve. And it turns out that my effect of doing better than what quantum mechanics predicts, it's about the photoelectric effect. So here, the photoelectric effect dominates over the Compton effect, and that's where we get rates greater than chance the best. Now, I've tried it in all parts of the spectrum with different isotopes. Over here on the left, the smaller pulses, it's harder to do because the detectors are noisier. The bigger pulse, like cesium-137, the Compton effect will dominate, so it's very difficult to see what I'm talking about. And there's several other isotopes here, and I've tried them up here. The first time I tried this, I was using sodium-22, and I did not see my effect. And then I studied and learned how to do this and discovered this property of the photoelectric effect in the detector. So if one was to do the experiment up here, you use a different detector that has the Compton effect closer to the photoelectric effect. And I've done that with sodium-22 successfully. So it's not a special case where it's just these two. I've seen my effect with 4 isotopes, actually, up and down the spectrum. But these two are the best where it dominates like this. The other thing about like why was this not been done previously is because of everybody is thinking in terms of photons, and I don't. I was looking for what's going on and trying to let nature tell me what it is. So let's do a little bit of history, a little review. I've shown this in previous lectures, but it's good to see anyway about like, well, what is a photon? The model of the photon is that it's not visualizable. Uh, this is in a famous book by Bohr of discussions with Einstein in this part of the book. Let me read this sentence. If a semi-reflecting mirror is placed in the way of a photon, leaving two possibilities of its direction of propagation, the photon may either be recorded on one and only one of two photographic plates situated at great distances in the two directions in question. Now that's part one. That's the particle part of the photon model. Part two. Or else we may, by replacing the plates by mirrors, observe effects exhibiting an interference between the two reflected wave trains. Okay. So let me go to my picture of this sentence. And pretty much everyone agrees that this is the way it goes on. So the beam splitter, if one thinks as energy held together quantized, well, you'd expect to show one way or the other at the beam splitter. And when you look at the timing, they'll be separated. We're looking at this timing. And here's the other part of the model of the photon. So I agree with this, that you'll get a interference pattern. This is the part that I think is right. But the first part is what I'm showing is not right. And so I'm showing this one way or the other property is well, they never really understood how to do the experiment. And I'm showing how to get the opposite answer that people did for this experiment. I'll show the history of this experiment. It turns out that I did a gamma ray experiment that I published in some of my patent applications and in physics essays to show that the one at a time source can create interference patterns. I did an experiment to show that it had to be interfering with electron layers to do that. I tried publishing as far early as year maybe 2002. I've been doing this since 2001, this experiment. I'm trying to publish in various ways. The publishers would not have me, so I thought, well, I'll show them. I'll send it to the patent office. And I sent them 20 experiments versus worth of data, and they did not get past the title, which is photon violation spectroscopy. And there's many discoveries I made with this spectroscopy. I invented a spectroscopy and also splitting the atom. Anyway, so this is the model. And so now some more history. Planck's 1900 famous work, he had quantized absorption and quantized emission. And people say he quantized light, but if you look closely at the paper, he quantized the energy in the oscillator being the electron. But this is the model that everyone has taken up, that energy is quantized, and that was Planck's first theory. Planck had a second theory in 1911 where he understood about the wave properties and he did this idea of continuous absorption and explosive emission. See, we don't get to see the absorption. We only see the emissions. It makes it difficult to do the experiments to tell what's going on here during the absorption. And and people did experiments with the element of time in the photoelectric effect. And if you use this model, it doesn't quite work out to fit the experiment because it implies that you're always starting from a zero place of loading up. And then there's going to be like more time. And the detectors in the experiments to try to see, well, does this loading theory work? You'll see in your textbooks, and it's in my previous lectures, the whole history as to how this was handled. they they're comparing to a model that doesn't quite fit reality. Now this is a correction model where, and Millikan guessed this model when he was exploring the photoelectric effect. It's the minute addition idea, where there can be an arbitrary way that electron can absorb kinetic energy, and it may only need a small amount to trip it over to the threshold, and then it'll emit and look like a particle hit there. And this is what I'm saying is going on. And so I expand on these alternative theories, and I have equations for it also. But that's what I say is going on. And the idea here is to show by experiment that this must be what's going on, that there's a hidden state, a sub-quantized state that you won't see unless you do my experiments, the experiments I'm outlining here. And everything will look quantized. That's why quantization is so popular. We only see these emissions. There is something sudden about the emissions. It does look like that. So, all right, here's the early experiment, the first experiment of the test of the beam split coincidence test. This was the first one. And they have an equation of chance. If you transpose the time under here, you'll get the same equation that I used. Rate, and a time constant equals the chance rate. So what they're doing is they're comparing to chance. So the rate of the experiment in the same time window that you calculate for chance, you take a ratio, you take the fraction. What is the rate of the experiment divided by the chance rate? And what do you see? They see that they're about the same. And this is what quantum mechanics predicts. And so we're going to do this equation later and see, well, what do we have? So anyway, they did it right as far as the equations and the idea of testing a beam split. But there were a few other things that were not quite right. The second time this was tested, here's the beam splitter. So they're using a dim visible light that goes to see if the photon model holds up to go one way or the other. They're using a similar kind of electronics that I use. Let's see, what are they doing? Coincidence. I did my experiment with coincidence gates in a similar way. I did several other kinds of electronics, and they worked as well. Before I developed it with the LaCroix, I did it with the same electronic systems that people of the past did. Here's what's important. The time difference histogram. So here they're inserting pulses of light to create coincidences, and you get this nice peak. But here is the actual experiment with the dim light where they're doing their test, and they get this band of noise, no peak. And so this is what quantum mechanics would predict. And they say so. If such a correlation did exist, it would call for a major revision of some fundamental concepts in quantum mechanics. So they have the right chance equation, the right way of graphing what's going on, and the right way of looking at a beam splitter. A lot of things right. But it looked like quantum mechanics. Then again, so this is Clauser's work testing.
Eric, if you would be willing to say, in both of those slides you mentioned under bad that the pulse heights weren't considered as part of bad. Could you just explain the impact of not recording pulse height data in those experiments and why that's a weakness?
Good. They did not record where they set the discriminators, where the pulse height discriminators, like I was trying to show before. There's no information as to where they set those. That's one thing. And I'll get to a slide about that, about here. So with a visible light, you do not get to really, you don't get to do a decent pulse height budget to say how much energy is going on. And also, they don't tell you where they set the filter, the discriminator. Like, where are they only looking at these big pulses? Well, if they do, then they're eliminating these. And so if you use the gamma ray, you get to see a relation to energy. But and in previous tests, they did the relation to energy by using the photon model by saying it was monochromatic light. This is monochromatic light, and all the detectors, like avalanche photodiodes and so on, they all do this, even if they're cooled with liquid nitrogen, unless you go to gamma rays, where you get to have pulse height resolution, and then I get to say I get this much energy. And I get to add the energies in the two detectors and say, oh, well, I get twice the electron volts from what it should have been to start with. It's a 2-for-1 effect. But we embrace energy conservation. And what it means is that it's not a photon that's landing there, that there had to be something ahead of time, like I was showing in Millikan's minute addition, to show that there's something there ahead of time, to embrace energy conservation. There's something energy here ahead of time, a little bit more, and then we get two of these, and we get twice the energy. So you get to do an energy budget. And so they're not doing the energy budgets when they use visible light detectors for a few reasons. You don't, the pulse height distribution is too wide, and they're not even telling you what pulse heights they're using. All right, that was a good question. So let me go back here. So here's what Clauser did. His strategy was to set up from a source that emits two H news in coincidence, and then to see on opposite sides of the lab that you get coincidences, and they were able to eke out that it did. And from that, they say what went in one direction had to be one at a time, and then they split it and see what happens in the same delta T graph as I showed before, and they get this band of noise. And so there's no peak, and it looks like photons where it held itself together to go one way or the other. And everyone was very happy because that's what quantum mechanics predicts. Then later in time, Aspect, the French team, did an experiment similarly with two H news emitted in a cascade, an atomic cascade. And what went over to the left is used as a trigger, and then they do a triple coincidence. Now, to do a triple coincidence, it requires using the triple coincidence chance equation, but they strayed from using that at this point in history. They don't use the triple coincidence equation, and I say that's a big mistake. There's no fair straying away from the triple coincidence chance equation. So to clarify that, I'm showing other papers that explain what they did and why and how, and they even say that they didn't like, and you'd have to read it. I try to make it clear here. So uh, it's going to be required to go back and read some of these slides that I put because it's complicated. But they come right out and say they're using a different equation. Well, this is kind of nutty. It's a triple coincidence, but this does not look like a chance equation. They're using a rate for instead of the time constant. So right away, it doesn't look right to me. And then they go further on and develop this other equation. They want to make it look like the coincidence rate here is less than chance, as if it was a particle of light that was forced to go one way or the other. They changed the chance equation and they claim that it went less than chance, and I cried no fair. The actual equation to use for the triple coincidence is here, and it's in many physics books, and I give the reference as to who developed it. The nuclear physicists used a chance equation, the two and the three channel chance equations regularly. This is well studied, and so there's no reason to not use it. And I even did it. I did an experiment where I had a triple coincidence, and I found that I was able to use it and even defy it by my effect. So they're using the wrong chance equation, the whole mess of them. And so it's a really strong statement, a strange thing to hear that I'm saying that the whole of quantum mechanics is based on these experiments that are using the wrong chance equation. That's where I'm standing. That's my claim. Look at it. Look at it. Look at the experiments, what they did. Excuse me. Anyway, I looked at this before. All right. Another thing that the gamma ray gives us is a much better way to determine a one at a time source. So the nuclear physicists do this, and here's their information about how it emits one at a time and what it decays to stable and stable. Cobalt 57 has two different routes, and they don't happen at the same time. So it's still a one at a time source. This is a slightly, uh, uh, let's see, which is more or less. There are two gamma rays that are close together, and you could just about see it in my spectra. So, and this is the setup for doing that test. So you put the radioisotope in the middle, in between a pair of detectors, and you do the timing histogram with the same electronics that I have set up, and so they do it the same way, except they're using it for testing if it's a one at a time source. And if it gets this band of noise in the delta T histogram, it's one at a time. It went this way or that way, but not together in time. If it goes together in time, it makes a peak. And you know that the radioisotope emits two at a time. So, and then I do the same experiment. This is the data that I had for the other isotope, cadmium 109. And this is the band of noise here. This is the delta T histogram. And the calculation comes out to when you do the chance, when you read how many are here and you do the rate 1, rate 2 tau and get a number and you read and compare the chance, the experimental rate divided by the chance rate is about 1, which what it should be, which is chance, to say that the isotope emits one at a time. That's really important. So we have a much better way of knowing what we're starting with than what anybody else does by using this tried and true test of gamma rays, whether it's emitting one at a time. An atom that decays spontaneously will emit one gamma ray, and then if there's another atom next to it or nearby that also emits, it'll only happen overlapping in time at the chance rate. And everybody agrees on all that, whether it's one at a time or not. Okay. This is a background test. So to do this experiment really fully, you have to subtract background. It's so I left this on. Somebody can calculate for how long is this? 22 kiloseconds. Anyway, that's several hours. I think it was, I forgot. So there are coincidences that will happen when the radioisotope is removed. So we use that as a background. We subtract this small rate, so you calculate how much it was, and 0.001 per second. And so that's within a time window, the 100 nanosecond time window, and we use that same time window in the experiment proper, and we use that same time window in the calculation of chance. So it's all symmetrical. It all makes sense. So those are important experiments. All right, now let's see. I can go back. Let's see how the experiment is doing. What's it doing? Oh boy, that's nice. That is a nice peak. Let me center it. So it's position. Oh boy. So we can actually do the whole calculation now. And 131 in 2.4 kiloseconds. So I'm going to write this down. Right. So webcam slides. Slides and I'm going to just go to this to the webcam, and I'm going to write down the equation. Now let me stop it. I'm going to stop the LaCroix. 134 and 2.45 kiloseconds. 2.45 seconds. 2 seconds. All right, that's the rate of the experiment. We're going to have to calculate that later. Now we're going to look at, well, what's chance? And so we're going to do the experimental rate divided by the chance rate. And the chance is this equation. The rate of one, the rate in two, and this time thing. And we're gonna get those numbers. Let's see what those numbers are. Well, we know this tau. Let's see, let me go to Canon camera. Let's do this. Now, I have these counters up above, which are pretty good. That does 100 average. Now, it makes it easier to use that. Of the 1 and 2. So 691 per second and 75 per second. Let's just try those. And we could even check and see how it works. 691 and 75 per second. And so,
Eric, can we see the board? I
right,
think you're
right,
ready.
right. Good. And let's go to the board. Good. Um, and then there's the time window. So what did I have in there? Uh, 50 nanoseconds per division, 2 divisions. It's 100 nanoseconds. We'll put that in. Now, if somebody wants to use a calculator with me, they can do all this and tell me, and we'll see who does it first. I'm going to do it. And so if somebody wants to do it, that's great. And you could just tell me what happened. But in the meanwhile, I'm going to see what happens. 134, 2450, 0.0547 per second. 0.5 times 10 to the minus 3, 0.054. Okay. Now what's this? 691, 75 times 100 nanoseconds times 10 to the 9 change sign times 5 times 10 to the minus 3. 5.18 times 10 to the minus 3 per second. And so I'm going to take all that and say, what's the ratio of all these? And that number, I'm going to go divide and then do reciprocal. 0.0547, 0.0547 divide, take the reciprocal, 10. So 10.5 times chance. Well, that's pretty good. And anyone could check my arithmetic. Oh, now I forgot to subtract background. It's so small. I mean, we could do it, but the background subtraction goes here. So you do minus the background, the rate of background. It changes it a few percent. So that would go here. That's how the calculation is done, to see the experimental rate compared to the chance rate. And do we do better than chance? Do we look at it the same way those first two people who did the right chance equation? And actually, the third paper I showed, where they did and the fourth one as well, that they did the right histogram. And so the histogram, it may be worth repeating, like, what is this histogram about? Where there's 0 nanoseconds, there's minus nanoseconds, and plus nanoseconds. So when the detectors go click, click, let me get myself here in the screen. Um, where'd it go? Webcam. There. Oh, that's right. Okay. If this detector goes first and then second, you get a data point here. If this detector goes first and then the other one, you get a point here. If it goes together, it builds up. And so everyone else will see this band of noise. If there are coincidences, which means there's a mechanism. There's some reason why it does better than chance. It makes a big peak here. And that's what we see. That's the experiment. That's pretty much the whole experiment. Um, back to the LaCroix. Oh boy, does that look great. We have There we go. We have these nice wings that show some chance. And I showed how to calculate against that before. Um, we see the pulse height histograms, and they're all, so I have it on digital phosphor where it records over, and you can see that there are only a few pulses here that are close. That would tend to, there would only be a few distorted pulses that show up, looks like two. So that's not a concern. It's not like we're having high count rates that would distort everything. And that is a problem. If the source is too strong, it gets in the way. That's not happening. And there were tests I did with other instruments to see this. It's in my website, the different tests I did. And all these are beautifully behaved. There are no pulse, but this one is at a much lower rate. So it's all fine. So where would there be some argument against me? I don't know. I've been looking and trying to argue against myself for 20 years to make sure that I wasn't doing something silly here.
Eric, could I ask for you to clarify or confirm the hypothesis is that the peak in the time difference histogram, as opposed to the flat uniform, is because many H nu are being released because of preloading. Is that accurate, or am I misrepresenting the?
It's not quite right.
Not quite right. Thank you.
Yeah, it's not right. It's that one emitted makes two in the detectors more often than chance. I'm showing that it's not holding together like a photon by the model that we started with.
I see.
We're testing this idea. Start with one. Does it go one, like one way or the other? Or can it go two? If it goes to two detectors more often than chance, it makes that peak. And that's what other people have been looking for when they did this experiment. They saw no peak, but now we do see a peak because we're doing it with gamma rays, and we're exploiting the properties of the gamma ray that let us see through the illusion of this photon model. So yeah, it's one at a time, one H nu, creating two. Well, you think, well, how do you get two for one? It sounds like maybe I'm getting energy from nothing. No, we embrace energy conservation. And we realize that it's that there's something there ahead of time.
Eric, I had a question if I could.
Yes.
You just showed a beam splitter in your device as the source of where you were getting the definitive numbers. There is there's no such thing as a gamma ray beam splitter that I'm aware of. So what are you actually using there?
There is such a thing as a gamma ray beam splitter, but what I'm using is a detector, and I've done it both ways. I'm using, I know I started by looking at a beam splitter because that's the kind of experiment. It's called the beam split coincidence experiment. But I'm doing where I'm substituting in this experiment, I'm using a small detector instead of a beam splitter. The small detector is performing the dual function of tapping off some of the energy, letting some go through as a beam splitter. What goes through is like what a beam splitter does. It taps off some of the energy, but it's also detecting it. Well, it's doing this dual function. So other people have done this. It's called a telescope, but they've never done it with electromagnetics. They've done it with muons and protons and other massive kinds of stuff to do this one in front of the other technique. But I'm the only one to do it with anything electromagnetic to show the defying of the proton method.
Hi, Eric. This is Carla speaking. So just a quick question as I'm trying to understand your theory here. So is then your hypothesis that this extra that you're calling ahead of time 2 for 1 is related to the radiation field present?
It's in the detection. It's in the detector. There's something stored in the electron. It's still my theory is it's really a theory of the electron. It's
Right.
it's that the kinetic energy in charge will load up, and that there's this hidden amount that we don't see readily as to what the kinetic energy of the electron is. It's
Right.
there ahead of time from noise or other gamma rays or whatever, and then it
Right.
reaches the threshold.
So I guess that's the question. So is that extra related to the radiation field that which is not seen within the electron that it gathers within the actual field that it resides in? Or is it related to, for example, zero point energy, zero coherent point motion? What is it that related to that is left in the detector that actually belongs to the electron that it picks up in its
You
environment?
had it right about 0-point energy.
Okay,
It is 0 point. This is a way to see 0-point energy.
excellent. Yep.
Yeah. And so that's what Planck's second theory was about.
Right.
And there was this extra h over 2 and h nu over 2 that
Right.
is used by other physicists, like low temperature physics. And that's where the 0-point energy came from. So that's what my theory is embracing, expanding upon. Yes.
Well, in low, just a correction, in low temperature physics, I mean, we usually think about zero coherent point motion. So for example, when looking at superfluidity and we're looking at, close to, 2 Kelvin or 0 Kelvin. So they're related, but they're slightly different, right? But when you think about the electron itself, then 0-point energy becomes a more quote unquote coherent concept.
Well, you're way ahead of me on that. I don't know much about it. I'm just pointing out that the concept came from Planck's second theory of 1911, and that's
Right.
what I'm expanding upon.
So would it be concise or approximately true to say that this 2 for 1 that you're seeing in the detector ultimately corresponds to the extra 0-point energy effect of the electron itself that is left over in the detector?
That's right.
Okay.
That's exactly it. It's in the electron in the detector that we're giving an extra push to go to the threshold, and then it shows up. It is 0-point energy.
Okay, so you and I should talk a little bit afterwards. Thank you.
Oh, great. Well, what's your name?
Carla Galdames, we've been in touch via.
Carla!
Hi, Eric.
Nice to hear you. Right. Please
Yeah, me too.
Come over and see the experiment.
I will for sure. I will stay in touch. So I'll continue to hear. We both, I believe, means Wolfgang Bear. But yes, I will be there. I'm working on 0-point energy field and zero coherent motion in superfluidity. And we're going to do some experiments at UCSC. They're not exactly related. They're about decay times of nanomaterials, but I'll stay in touch. Please
Well,
continue.
you
Wonderful.
can do my experiment.
Yeah, let's try it out.
For sure. And I'll meet you in Sweden.
No problem. Let's go there together.
All
Thank
right.
you. Okay, I'll stay here.
All right.
I got some more query there, Eric. You talk about this
Louder.
from one. Is it possible to do
Louder. I can't hear.
3 for 1? I was asking, can you hear me? I was saying,
Yes,
you did the experiment, getting 2 from 1. Can you do three from 1?
yes,
And
yes.
have you done that
I have
and
done
get
that.
similar results?
I have done that and seen similar results. Yes. Uh, uh, I can go to my other lecture and show the actual data of some of that experiment. I did it in last week's um, let's see if here it is. Let me get this up. So slides, that should be it. All right. So it's in photon violation spectroscopy where you use one detector as a trigger for the other, and then look at the pulse height spectrum. And you see what happens in the pulse height spectrum when you trigger it. So here's one here, and here's two. So this is 3 for 1. So this peak in the pulse height spectrum is so the horizontal is the pulse height spectrum of this detector, the second detector. This peak is triggered by the other detector. So that's 1 and 2. There's 2 detectors. So this peak is also already a 2 for 1. Then this is a twice high peak. And you calculate out, well, how often does that happen and so on, and it defies chance. And this is a 3 for 1. There's a hint of 4. So this was done, let's see, I did this as far back as 2002, and sodium iodide detectors. Over here, I used the high purity germanium detector, which is pretty interesting in that when you do the single spectrum, you do not see this extra twice high peak in the spectrum. But you do it in coincidence. And so there's the peak in the germanium detector, but it's triggered by the other one. So that's 2 for 1. Then here is a twice high, so there's a bigger pulse. It's twice as big. What would make that? 2 of these. That's 3. So I just do see evidence of 3 for 1, and I've done it in 2 different detector setups. So, right, if it goes 2 for 1, you should expect it to do 3 for 1 as well, and it does. And so there are many variations that I've done to sort all this out, and
Right.
all the different ways.
Hey, Eric, Dave Chapman here.
Hello.
Yeah, I got a couple of questions for you. Now, when the gamma ray goes through the first detector, it gets detected by interacting with the material and transferring some amount of energy to the detector material. How much energy on the average gets transferred to the detector as part of that process?
We don't see just that fraction at all. It's very difficult to determine what fraction gets tapped off because we don't know this initial state. There's this hidden 0 point energy state. We don't know the level of that to begin with.
Well,
To
generally speaking, if you've got, an 88K EV gamma ray, and each of the electron hole pairs or whatever that's generated has on the order of 1 to 10 electron volts per electron minority carrier, whatever it is that gets created, then, if it loses 1% of its energy in the detector, you're going to be looking at maybe several hundred, maybe 1,000 minority carriers.
yeah.
And so the second question is, given that you're probably going to be looking at on the order of 1% of the total energy being consumed in the detection process through the first detector,
Yeah, yeah, yeah.
what effect do you suppose that's going to have on the polarization,
Yeah, yeah. Look,
travel time,
Dave,
energy?
Dave, I know just where you're coming from. You're still thinking like a photon. You're still thinking, yeah, frequency is conserved, but the
Frequency
amount
is conserved. Okay.
frequency is conserved as it goes through. And it's that Planck's constant is a maximum, is what the ending up of all this theory is. Like, how do you make it all work?
Well, is there any scattering? Do you have any changes in the direction of travel of the wavefront, or, is the total momentum affected by this interaction?
Yeah, uh, I try to do as a function of angle in this experiment, where I would
Right.
have
Okay.
coincidence and I would scan over. It's hard to do, but I did
Yeah.
try. But I I'm coughing.
All right. So you did go looking for that, and
Yes, yes.
and the yeah my guess would be that it's a very small effect, and it's going to be hard to identify.
Well, what I did in this experiment is that it was crystallography where I really changed the scatterer in a few different angles to see that it changed the quantum effect rate. So I didn't try a whole bunch of angles here. Uh, I only went as far as to convince myself that there was a Bragg reflection involved in the scatter. So how it goes by the direction, it's Bragg reflection. It's just like X-ray diffraction Bragg effect. And so I did some calculations on it where by the de Broglie wavelength and the angles and stuff, it's not about the spacing between the layers of atoms the way X-ray diffraction is. It's about the structure of the electron itself. So we're able to see that in this form of my spectroscopy. And that's getting towards the answer to your question. How does it determine the angle? It depends on the crystallography of what you're scattering off of.
So in the usual version of this experiment, the angle is very small, and to first approximation, you're not going to be able to see it in your data set.
Well, I set it like at 30 degrees, and I'm not sure if it is so small, but I
Okay.
I
Well, I'm more interested in the case where the gamma rays are going through the first detector and then through the second detector, in which case the angle is more or less zero.
oh well,
Um,
yeah, it you don't see angle in that geometry.
right.
You don't get any information of angle. You have to use a separate scatterer to figure out the angle of scattering like this.
So, and are you able to observe any you know, spread or attenuation or variation in the energy of the gamma rays coming out of the first detector?
Uh, well, that is in the spectrum. Yes, I did, and
Okay.
and I was able to see that. I did that here on this slide where there were whether it's paramagnetic or ferromagnetic or with and without the magnet, how it changes the scatterer, and
Oh,
how the scatterings and whether it's Compton scattering or Rayleigh scattering, whether the bond is a stiff or flexible bond. So I was able to see by the amount, the positions of what happened in the triggered spectra. It changed as a function of those things I rattled off here, and
okay.
and also as a function of the crystallography of the source. it changed the spectrum and also the temperature of the scatter. So I did all these experiments to try to figure out what makes this thing tick. And that was way back. That was, I have some dates on here, but it was like almost 20 years ago I did all this.
Yeah, okay. All right, well,
It, thank you. It's all documented. I called the paper photon, here it is, photon violation spectroscopy. And yeah, that's about all the different. But what's most important is, well, let's get somebody to do the very first version to see if it just works at all in somebody else's lab, like Carla, if she can come over and then I'll visit her in Berkeley and we'll get it all running over there, and that's what's going to be really fun.
Eric, this is Terry again.
Hello.
I couldn't quite hear you. Some of the first time I got a flurry of beeps that I couldn't shut off, so I'm not sure I fully followed what you were saying. You did just show a figure where you showed a crystal as being a beam splitter. And I have to go back to this one point. I am not aware of any situation in which a crystal of any sort can coherently reflect gamma rays. Those work at the nuclear scale. You can do it with X-rays. And with difficulty, you can do it with X-rays. But when you get into the gamma ray spectrum, you're just getting direct interactions with the nuclei of the atoms. And I'm not aware of any coherent phenomena at that level. Just building X-ray telescopes is an incredibly difficult thing using very low angle reflections. So I'm not sure what you mean when you're talking about like Bragg reflection, talking about gamma rays, because they don't do that to the best of my knowledge. So I'm trying to just understand what you're saying.
They didn't. I did it with looking at the unquantum effect, so it lets you see things you would not see otherwise. Nobody did it in coincidence, the way I'm saying. So
No, but I'm trying to understand the materials that you're using. Like you showed a crystal of what was what, and I think you said it, but
I didn't say it. In that case, it was silicon.
okay.
So I tried a few different scatters.
Okay, they are scatterers, but would you agree that they're not coherent reflectors? They're not partial mirrors for gammas.
Well, I'm not so sure. I think it is like a Bragg scattering, but spacing
Yeah,
doesn't make
scattering,
sense.
yeah,
The,
scattering at the nuclear level, though. So
yeah,
again,
yeah.
I'm not
Stop.
aware of it because the spacing
I,
between the atoms is so huge compared to the gamma
I
frequency.
know that. It wasn't about spacing between atoms. It was you had to be too high a order for it to work that way. I did that calculation.
Right,
And
right.
so I wrote that up. And it's about the structure of the electron that is the scatterer. The electron has a periodicity, is what it discovers. That's what it looks like. So my theory is really about the electron, is that its envelopes, that the de Broglie wavelength is really the length of an envelope, not a phase wave, and that inside the bond structures there'll be these layers, and that I did these experiments to see it, to see, like I tried to show with the magnetic field and the temperature and the rotating of the crystal. It all made sense at the time. So yeah, it's a whole different thing. It's about the structure of the electron itself that has this periodicity.
So what you're suggesting is that an electron, when you say electron, I'm interpreting that as an electron orbital. So electron orbitals in silicon have a quantum mass frequency. Is that what you're talking about? Because that would be certainly would be a different frequency from. I'm reaching it because I don't know what that means when you say an electron, structure of an electron.
Yeah,
Can you elaborate a little bit on that?
yeah. Well, it's the charge wave.
Electron orbitals?
It's a way of seeing what these orbitals are, how they interact with gamma rays.
Okay,
It's a
that's
way
kind
to
of what I was
explore it.
asking. That's kind of what I was asking.
So, for one, you go back as far to any kind of electron diffraction experiment, and you'll be in wave-particle duality if you don't look at, well, what is the wave nature of charge? And so I did some calculations on that, like relating what they call the de Broglie wavelength equation to the photoelectric equation. And so I derived the photoelectric equation. And I used this envelope method where, I don't know if I have a slide for that. And I made it fit to several different equations. Let's see. I thought I would have a slide. I'm going to go to this slide. There's a wave nature that is generally overlooked in quantum mechanics. I mean, they just assign it to a probability wave. But then you get into this problem of the wave function collapse. I'm showing it's not like that at all. There is no wave function collapse because the experiments that lead to that were done wrong. I get the opposite answer. I show what they did to, and how to see a different answer. So it's not that it goes one way or the other, guided by a probability wave, that there is a wave structure in light, and then there's a wave structure in matter. So in this experiment actually helps my case to where my beam split experiment is not just with gamma ray. I had good success with the alpha ray, the matter wave. So, it was very hard to do the experiment with electrons. I just skipped over that. So I did it with alpha rays instead to show the wave structure of the matter wave. But what happens here with the matter wave of the alpha is the same situation as the electron, that whatever goes across space, if it splits to go 2 for 1, and if it diffracts, it really is a wave. It's not a particle. So it's a different way of thinking about the whole business. And so I'm backing up what I'm saying by these experiments. Nobody did this.
On this figure that you're showing, that's a I know that you're strong in conservation mass energy. That's one of your fundamental principles. But you are showing two alpha waves. You're showing two helium nuclei, showing one helium nucleus lining up in two places. At least looks like that's what the figure is saying. Is that what the figure is saying?
No.
What is it saying?
I'm saying it's a 2 for 1 effect with the matter wave. That you're starting with 1 and you're getting 2, because it's not a particle when it splits like that. If it shows wave properties, it's not a particle. I'm making my case.
Well, when you make the detection, you're showing the detection, those purple dots.
I know all that.
Well, then is that 1 or 2 alpha waves or alpha particles or alpha waves? But either way, when you detect it,
you missed the point. You missed the
capturing
point about the loading theory, about the accumulation. And we spent a lot of time a few months ago, and
your point is a loading theory, that there's like a background accumulation of helium nuclei-ness in both plates, and then the triggers. So
that's right.
Helium.
That's right. It's actually heliumness, and it's helium loading up to a threshold where I'm getting 2 for 1, starting with 1 helium nuclear wave function, 1 emission at a time, and getting 2. So I have the data for 2 for 1 with helium.
Okay, so
very sensational result.
To get back to your point about that, because true, you do believe in complete conservation mass energy. Is that correct?
Yes.
Okay. So getting back to that, I would interpret the diagram you're saying as this is not an isolated single emission case. This would be a result you would get after a long accumulation of alpha rays. You would start getting results in which suddenly you see briefly ones where it seems to violate energy or the conservation mass energy. Seems like you're getting two, but that the total sum still stays the same for the overall sequence. Is that roughly right?
It takes several hours to do this experiment. It builds up.
That's what I meant. Because see, if you look at this figure you're showing right here as a single incident, and that's it. You have complete control. You have one alpha wave comes out and it winds up in two plates. That violates mass energy conservation because alpha waves, by the time you detect them, they've been attached to something. It becomes an actual helium atom.
It's
Conversely-
I'm defying a particle energy conservation.
Well,
I'm not defying energy conservation altogether. I'm
Right,
showing that it's not always a particle.
I'm trying to understand you, and that's where I'm saying I'm not trying to disagree with you on this. I'm trying to understand your interpretation, and I think you did agree with just what I said. This takes hours. This is not something that happens on a single incident.
Well, sure. I'm putting together 100 incidents here.
Okay, right, and then you're getting this. Okay, so like you say, the figure by itself, just sitting here staring at it, it's hard to tell that. But the figure on the right, yes, if I look at that and look at the detail and said, yes, 100 accumulation. Okay.
All right, good.
I feel like I have a better idea of what you're. Oh, one other question I had. You said something about, someone mentioned that you have a 1% drop due to the scattering effects on that. You're going to have a frequency drop, aren't you, on the gamma ray if you have some kind of scattering incident going on?
Well, sure, the rate goes down going through some material.
Okay.
But what I'm saying is going on is that the frequency of the gamma rays are conserved, and that Planck's constant is a maximum, the way it works. And to really tie it all together, like with this atom experiment, it requires taking this idea of Planck's constant as a maximum and also applying it to the mass constant and the charge constant to understand that in these experiments that display wave properties, uh, like the alpha split, what's conserved is the ratio of our constants. So it's an unusual concept, but this is the theory that the constants are thresholds and it's the ratios of those constants that are quantized. And so if you look at the structure of the equations that are famous for wave effect, you'll see these ratios that the experiment doesn't give you the individual H's, M's, and E's. It gives a ratio. So all I'm doing here from the left to the right column is rewriting the ratio as a Q to emphasize that this is the message of the experiment. And that when they do the Compton effect, for instance, you'll borrow the H and the M from other experiments that isolated it out, like what J.J. Thomson did or someone, or the Millikan oil drop experiment to get E. And then you'll insert it there. So it's about understanding what is the message of the experiment and then seeing how nature is telling us what it's telling us when you have these wave effects that the ratios are conserved, and then when you try to figure out what's going on when you have a matter wave smearing out all over the place, and how does it work with all of our experiments? What I'm saying is going on is that if there's a release of a matter wave packet, that if you were to look at any cubic volume of that wave packet, you'll have some charge and mass, but it won't be the whole E and the whole M. But the ratios will be conserved. So it's a way of understanding the property of the matter wave that gets spread out such that the identity of its type, like if it was an electron or a proton, whatever, that it's the ratios that are conserved in the wave that gets sent across to the absorber, And then it could load up accordingly with that ratio and make it look like a whole particle landed there. But really, it was just that it loaded up heliumness or electronness to the threshold. And so this is really the trick. This is what made it all work. I figured this out in year 2000. And once I saw this theory, I was inspired to go ahead and build all these experiments.
Eric, I have to admit, when I think of the matter waves back to de Broglie, um, I would not see any difference in terms of saying that there is a helium particleness in some section of the wave. I think, in fact, I think if you actually asked, well, yeah, because the behaviors of those parts interpreted as wave, like under diffraction, still retain the uniqueness of whatever that is that's being diffracted. An electron still has electron-ish character when it's interpreted as wave as would an alpha particle. So
That's right. When
yeah,
you
I think
see diffraction,
I certainly wouldn't disagree with that. I mean, whatever matter waves are, they retain absolutely the uniqueness in terms of a number of quantum numbers of that. They kind of have to. Now that's a different statement from the threshold issue.
well,
Eddington was into thresholds. I didn't know that. Did you know that?
Eddington. No, I didn't.
Well, he wasn't. I shouldn't say he was into them. He looked at them, but Eddington looked at and assessed the threshold model, which surprised me. Because he was looking over a thing about how does a photon get into a telescope, and going through the whole discussion.
The, the
Question.
photon argument was
Yeah.
done by Lorentz. I mean, the telescope. Telescope argued against the photon.
Yeah,
Lorentz argued against the photon with a telescope argument.
and Eddington adamantly did, because Eddington was an astronomer, so he was just pointing out, said,
Yeah.
all right,
Well,
it's just
look,
this is
many
act like a
people.
wave.
Right. Look, it's obvious. Many people argued against the photon model, but the problem was, how do you explain the particle properties without this probability wave? And that's what I'm attacking directly, the probability interpretation.
Now, one of the things when you say you're going after the probability interpretation, at least to me, it seems like you're loosening up the definition of time. I would actually, I get,
Time.
what's that?
Time?
Yeah,
I
because,
like time.
well, no, I know you like time, but yeah, I think you're especially the threshold model, but you're getting, because of the thresholding model that you're using, you're getting alpha particles appearing at times in which a strict temporal sequence would not allow them to appear. So I realize I'm reinterpreting what you're saying a little bit in terms of the threshold model, but I can't help it. I keep looking at it and going like, oh, you're saying that if you do enough of these in a row, you're getting results that don't match a very strict particle. When you have a particle, particles are very strictly bound by time. They're saying, it either goes or it doesn't go. So it's just
The initial release is sudden, it is quantized. There
right.
is a quantized emission. But when you get to spread over space, the wave packet doesn't have to hold itself together. And then you could get diffraction. And then if you try to still embrace the particle and probability, you'll have this collapse of the wave function problem. So we're getting around that to show that you can get more than one responding from the wave that is initially released suddenly, and then you get a sudden absorption. So there's quantized emission and quantized absorption, but not always the transmission through space. Now, there are other experiments that I point out to about, well, is it always held together or not? And it isn't. It's as if the matter wave is a soliton where it there's a beautiful experiment that showed that by other people that it can hold. It doesn't have to hold itself together like that. Let's see if I can find that experiment.
Eric, I just want to tell you that
Here.
Carla has been asking you questions on the chat in real time at various points, but not saying them. So you're gonna have like 10 questions there when you get to it.
Okay,
Oh,
good. Let me just quickly finish this idea that there was an experiment to show that there's a signature of a particle going through a diffraction grid, and that the same source will also focus helium as a wave. So it's a two-state solution. The matter wave is a soliton where it could hold itself together as a particle, or it could lose that ability to hold itself together and focus. Now, this could still be interpreted by the probability interpretation, but this defies the probability interpretation to get to the two-state solution of a soliton. So I want to kind of leave it at that and go back to see what Carla is trying to ask. I don't see the chats. I'm not all that sophisticated here to see, well, what are the chats? I think I lost what I did.
Hello, hello, hello. Hello, hello, hello.
Yeah, we hear you now.
Can you hear me?
Yep.
Are you able to hear me?
Yes.
Yes. Okay, great. Sorry, somehow my speakerphone was not working. I am connected to different computer desktop here. So several questions, Eric, but maybe let's start for the last one. So what exactly do you mean when you say the same transition through space is not always the same transition through space? So what aspect of this detection is not sequentially temporal?
I don't know what you mean by not temporal. It's about whether the matter wave holds itself together as a particle or not. It'll go across space with some velocity, but is it a particle that holds itself together or not? This experiment by other people showed that there's a two-state involved, that it could still hold itself together and not diffract. And then there's also a diffraction signature. So it's just regular time, but it's about whether the wave packet holds itself together or whether there's a collapse of the wave function. So I'm saying let's dispense with collapse of the wave function. That's asking too much. The wave function has to go everywhere and then mysteriously disappear. But if you have this idea of a loading up, as if the collapse was inside out, it's like that. It's like a building up to a threshold and showing up microscopically instead of macroscopically falling down to the microscopic. So in a way, it's like saying the collapse of the wave function is inside out by having this preloaded state that can explain this matter wave experiment. This is a much harder experiment to do. I'm not set up to do it, but I did it many times in many ways of splitting the alpha. It's a more sensational experiment to split the alpha ray to show a 2-for-1 effect. Most of the time, it split in half. It had half height pulses. And so the pulse height is still about the characteristic of the alpha ray, its kinetic energy. It looks like what's happening here is that the kinetic energy gets slowed down in the interaction with the gold foil. And so you get half height pulses in each direction. But here, there's full height pulses. And so that really proves my point that I got 4 times accidental chance to get full signatures of the alpha ray to say that it's not a particle that goes one way or the other. It went both ways. And so similarly, like what I displayed with light, the first step is really to just understand getting around energy quantization and just doing that experiment to see well, what's really going on with energy conservation? This is another picture of the alpha ray split where I had it going over to the side. So I did many different geometries, different kinds of foils, and I even tried splitting it with gases. And there were some weak effects, but two layers of pure gold worked the best. And so I tried different kinds of different brands of alpha ray detectors and like different geometries. I did this experiment. I may have done it 100 times in scores of different ways to prove to myself, and rebuilt the whole vacuum chamber several times. And so it was a massive effort, and it was done. I did it about uh, maybe 18 years ago, and telling people about all these experiments ever since.
Right. So I guess that there's a lot of questions, but on the understanding of this concept that you're proposing of the wave function collapse inside out in the threshold model, do you mean it to be inside out because somehow as you're approaching this threshold, somehow you're beginning to select what's, for example, eigenstate of your wave function you're going to be detecting at your detector?
Yes, that's right. It builds up to an eigenstate from within.
Ah, all right. So holding that thought, and is that building threshold dynamics what you would consider then to be the structure of the electron, or corresponding to a descriptive aspect or mathematical descriptor of the structure of the electron?
Yes, I did some work on the structure of the electron by doing derivations of several famous equations. Um, I did a derivation of the black body spectrum using this envelope model of the charge wave. Uh, uh, there's an inner wave, which is Schrodinger's psi, and the envelope of psi is how light interacts. And so there's a derivation of the photoelectric equation that I did with this model. And also to identify the antimatter is that the phase of the inner wave is the opposite and that they can cancel out. And I tried doing some work with how the envelope would have a maximum of H. There's an area of H equation that Sommerfeld used that I embrace, but
Mhm.
but I'm taking Planck's constant as a maximum so that it can build up and then show itself as a discontinuous event, as if a particle hit there. But the area,
This sounds similar to sort of arguments of Zurich on the Planckian regime. I mean, in essence, it really kind of points at the possibility of this wave-like motion inside your envelopes to be directly related to vacuum fluctuations in the ground state of the electron.
who was that?
It's Carla.
Oh, Carla. You mentioned the name Sirius.
Zurich.
Oh,
Zurich's Planckian regime. I can talk to you about it later, but
all right.
um, but there's the theoretical frameworks talking about what happens at the Planckian level, right? And Zurich happened to be one of them. But in essence, I guess the question that I'm really trying to get to is this nature of the electron that you're talking about seems to be directly related to sub-Planckian fluctuations that which might actually be describable as vacuum fluctuations in the ground state of the electron.
You could try to use those words. That's all right. Yes. So it's that Planck's constant is about an area, but the frequency determines its shape, like the frequency of light interacting with it and the electron of the envelope determines the shape. The maximum, the maximum of the shape is determined by H, according to this equation, but that it could be less, and you don't see it until it builds up to that maximum. And so that's what I'm saying is going on inside for the theory of the electron, that there's shapes involved described by Planck's constant as a maximum, that there, and I'm just starting to repeat myself. I did some theoretical work on this and tried to make it fit. So everything. This is my derivation of the photoelectric effect, which is where I started pretty much. This is what's really important. So you start with the de Broglie equation. You could do it either way. You could start with the photoelectric and get the de Broglie, or the de Broglie and go either direction. I actually don't like calling it the de Broglie equation anymore because it changes the definition of the wavelength. It's really a wavelength equation. It's the length of a beat. So I'm taking the length of the beat as primal. And I actually, if you look back to Schrodinger here, he was hip to this, that the light is interacting with beats. So when I had this idea, I went and looked back to see who else was thinking this way. And I found Schrodinger. He had it right. Except there was a factor of 2 correction that I'm doing in how light interacts with charge. He's saying light is interacting with beats in a one-to-one way. But there's a factor of 2 correction when you realize how light will push charge and fit a beat. So there's 2 beats per light wave. And so you can make this fit with a few simple ideas with velocity equals frequency times wavelength and stuff. Then you do a little bit of adjusting, and you get the you get, let's say I started with the photoelectric effect here, and then I derived the wavelength equation. So I went in that direction in this write-up. And you could go in either direction. But you use this construct of starting with the photoelectric effect and understanding what the experiments are telling you about it. You end up with this corrected wavelength equation, where the wavelength is now the wavelength of the group, and it's not a phase wavelength. And so then what I did is I used that in the derivation of the Compton effect here. That derivation is here. So you start with this corrected de Broglie equation, and then you use the Bragg. So this is actually very close, just about the same thing as what's in Compton's book. This is kind of fun. Compton had a wave derivation of his effect, but it was kind of clumsy, and I'm cleaning it up by using this corrected de Broglie equation. But the steps are pretty much the same as what Compton did in his book. So like I have different words around it. So you use the Bragg diffraction equation, and then you juggle it a few times, and you use the Doppler shift equation, because when light pushes charge, it pushes it away. There's a Doppler shift here. And then you use this trigonometric identity, and lo and behold, you get the right equation. You get the Compton effect equation of scattering. So what's also beautiful about this is that the whole model, it predicts that there's another wave here that can go unscattered. And you can see that in the spectra. It's sometimes hard to see, but this is the wave derivation of the Compton effect. And in the history of physics, they used the Compton effect to try to say, well, it had to be particles because they had a particle derivation of that effect. Where did I put it? Anyway, you all know about that. There's a particle derivation, but this is a wave derivation, and so my point is that there are different ways of deriving uh, the same equation with different models. And so that's the trick, the secret of doing all this sorting out, like how to do physics, how to make a model that's consistent with as many different equations without having to do wave particle duality and the probability wave and all this many worlds and collapse of the wave function, all that nuttiness. And you may have another question. It's really nice to hear you, Carla. Thank you.
Eric, I was wondering if you could say something about the number that we measured or derived in the experiment, that factor of 10, which is standing in for the 6.47 on your slides. Is there a sense of how the experiment could be varied to determine the factors that impact that multiplier on chance? What are the things that you would expect would impact that, and how would they sort of validate the preloading theory?
Okay. So chance is pretty straightforward. Everybody uses the same equation. If you go to Knowles' book, Radiation Detection and Measurement, it's scattered throughout the book. They all like it. It's all done pretty much the same way. Sometimes there's a factor of 2 in front of it, depending on the electronics. But what you have, it's the rate. It's just this simple. But to end up with the final comparison, there's just everything about the experiment that will affect it. Uh, the, the thickness of the first detector compared to the second detector, whether you're missing things or how close it is to the source to the detector, everything affects it. Like, why did I see 10? I mean, just earlier today, I saw a different number because the source was a little bit ajar. It was in a different place, so. But if you keep everything the same, you get uh, uh, it reproduces, and so it builds up. Like you leave this on for not touch anything. You leave it on for a few days. It just adds more decimal points on here to say it's a more accurate, closer to whatever number near 10. But I've seen numbers up to like hundreds of times above chance. It just depends on how you do it. And so I tried sorting all this out. Uh, I found that there were effects of the crystallography of the source, the distance of the source, which detector, the kind of detector, the position, the geometry, everything affects it. And so it's a wealth of spectroscopy to see, well, what are these gamma rays? You do different things, you see different things.
Thanks, Eric. I just wanted to say I appreciate your work, and I've been following it for some time, quietly. And this is the first time I'm seeing you live, but I wanted to say I appreciate what you're doing and the courage it takes to do that. And I've been trying to contact you on LinkedIn and academia.com, but I haven't yet managed to. So please check your email on that when you get a chance.
What's your name, please?
I'm Bilal. My first name is Bilal. Last name is Khan.
Bilal Khan?
Yes.
Could you spell Bilal?
Yeah.
All right. Well, at uh, at the bottom of my I, I think I had my email should be down here. Here it is. ES. Now that's not just being displayed. Let me display it. At the bottom of this slide is one of my emails. ESWriter 2024 at thresholdmodel.com. So I'm very thankful that you're communicating.
Eric, are we going to be getting a copy of this communication of this recording?
Yes, it gets posted, and they the company that puts on the show posts it. I put links on my website to all these videos, so it'll take a few days, whatever it takes them, and this recording will be at the very top of thresholdmodel.com.
Okay, great, excellent. I just have to add to Bilal's comment that yeah, excellent. I mean, it takes an incredible amount of courage, perseverance, dedication, and vision to continue the work that you're doing. So thank you for your work, and I look forward to communicating further.
Thank you.
Eric, can I ask another question? It's maybe a bit silly question. I I just wonder what the transmission median, what effect would the transmission have on your results? So I imagine that hypothetically, if you're transmitting your pulse in a vacuum, would
Right.
that to have some effects, or the medium itself has some kind of internal resonance at the electron level, which alters your responses?
Well, for the alpha ray experiment, it is in a vacuum. It doesn't have to be a high vacuum, some crude vacuum, but I had a turbomolecular pump doing high vacuums like 10 to the minus fifth kind of torr. So it's not critical. It's not critical. It's the kind of gas. I did try to do a gas, like I put propane in here without the gold foil and was able to see some scattering like that. So if you put gases in the matter split, you are able to see, but it's much weaker to see a gamma a alpha ray split. Now for the gamma ray, it hardly matters at all. It's just air. Gamma rays go through air readily, so it's not important.
Yes, fine. Thank you.
I'm looking at an older lecture here. This is a few months ago. These are the lecture slides I had, and so uh, please, there's much detail, a lot of work I put into these lecture slides to show the theory and the history, and you don't have to believe me. I tried to put it in a way where you can see what the history was, what's in our textbooks, and the kinds of thinking that was going on towards how it left us with what looks like quantum mechanics must be right. This one is the derivation of the de Broglie equation, and I point out that it didn't have to be this way. There are problems with it. There's details here to see. So, right, the best writing of mine is in these lecture slides, which will be at the top of thresholdmodel.com. The last few sets of lecture slides is really my best writing. There's putting together the history, the theory. Um, uh, what did J.J. Thomson do? You'd think, well, it's a done deal. E, you get the charge of the electron. Well, what do you do with that? Is the electron constant a threshold also? Why does it always look like a threshold? I answered questions like this. And what happens when you diffract it? It's in a different state of matter that will show its wave property. And so I addressed these issues. So it's not a one-liner. This work. This I had to dig back into history. This is a nice cartoon. Like, what is this loading model? It's like filling cups. I like doing I like doing this skit. So I'm gonna try to end my my spiel here with this little skit. The loading theory is like cups. Pretend that you have partially filled cups and that it's a rule. You only see what's in the cup when it's full and then it all spills over. I'm saying let's just take that rule. So you start with a full cup over here. You throw it over here. And then, oh, wow, now it gets full. Now that it's full, it could spill over. This is the 2-for-1 effect. One turning into two. What was that? There was already stuff in the cup to start with. That's what the end result is, that there had to be something there ahead of time in order to get a 2-for-1. And so that's what the experiment's showing. Exceeding chance is that it's getting 2 detectors more often than chance, the same way other people were looking for it. And argue with the experiment.
Eric,
Yes.
can I mention the usual counter to the threshold just for reference?
What's the
Well,
counter?
because it has been, the idea has been explored for literally over a century. The problem people always catch on is that preloading, because if you have a single particle going out from an emitter in an isolated experiment, a single alpha particle, and you have a spherical surface at a certain distance out there, as far as I know, from every experiment people done and stuff like that, they will detect exactly one alpha particle eventually. Now that's different from what you were describing with the whole series. But I'm just saying that if you put it that way, you have to ask the question instead, where's the preloading of the alpha particles coming from? Because that sphere could be a mile wide, or it could be the size of the solar system. And yet,
if you look at the periodic table, you'll find helium in everything except
oh,
hydrogen.
yes, but I'm talking about one particle inside of a sphere in an evacuated chamber. This is an experiment somebody can do to make it a foot wide, and you will see, as far as I've ever heard from experiments, one alpha particle. So you have to ask about the preloading. If it's going to be a preloaded, everyone there has to be right at some threshold where it finally hits. So do you see what I'm asking?
Usually you get the alpha goes one way or the other. Usually it is just
Well, that's a
one
particle.
way. It doesn't always split.
But alphas are waves. They're not particles. So
That's my point, that it's a wave,
yeah, but
but it doesn't always split.
when you say it goes one way or the other, that describes it as particle. And the trouble is, it is a wave. It is a radiating wave going outward from that point. So that Are you,
Look, this is really confusing. Most people will say it's a particle guided by a probability
oh,
wave.
I'm not most people in that part.
All right, well, look, then we agree that it's
Yeah,
spreading
know
like a
it that
wave.
way. Yeah, I'm in the curious position of accusing you of saying it's a particle. So yes, that would be a little unusual. But the preloading is, and like I said, I'm very much in the wave camp. It gets trickier for larger objects, but yeah, it's a wave. Anyway, just for reference, I was just saying put that in that because if people look this up historically, uh, Eddington would be an example. That's where Eddington went through an article and said, like, yeah, I don't understand how it gets preloaded. So, and that's not saying it's insolvable, but if you don't look at the problem and say, well, what's the counter? It's hard to make further elaborations on the idea because you just kind of get stuck there at that point. So, the preloading issue is certainly the one historically that has most often come up when this has been contemplated by, and many people have looked at it. I agree with you. There's a lot of people have looked at this idea. So it certainly has a strong heritage in terms of the quantum theory at early points. But
I haven't found anyone who understood Millikan's idea of a preloaded state that is close to the threshold that only needs a minute addition. Everyone else,
I have not looked at Millikan's. I'm not familiar with Millikan's interpretation. I've seen some other authors that have written about it.
yeah, well, look, I looked high and low, and there's sure to be somebody I missed, but I couldn't find anyone else that had a loading theory where it was an arbitrary way to get to the top. They all start from zero and they try to figure how long a time would it take to load up, and they'll have an element of time in the photoelectric effect test, and it'll be in all of our textbooks where they'll say it takes a minute to load up if you do the calculation, but it can respond in a nanosecond. And so they say, therefore, it has to be the probability interpretation of quantum mechanics. But they're using a model that is not workable. They're not using the model where there could be an arbitrary way to get to the top. To show me somebody else who does that other than this one line I found in Millikan's text in his book about this. Let's see if I can find it, where he considers the loading theory. Let's see, where is it? Here. It's not on the screen. And so um, this one. So this is the first place I've seen where somebody had a workable loading theory. Where in Millikan, it's in both his paper on the photoelectric effect and in his book on the electron, titled The Electron. Well, here I say. Needed but a minute addition at the time of the experiment to be able to be ejected. Right. So he gave up. He didn't see how it could work.
Right.
And,
I have seen this. I have seen this one.
oh, good. So,
But I also kind of wound up the same place he did. Like it's terribly difficult to conceive. So I could empathize with his point with that because
right. Well, to make it work, what I found that you need to do is to threshold charge and mass as well as action. So you start with the way Planck thresholded action, then apply it to the other two constants, and then you could make some sense out of the world. And so that's what I did. I did this theory in year 2000 and tried telling people about it. But the experiment drives it home. So, how else would you get the results that look like 2 for 1? You start with energy. Well, what's going on with energy? You could just about get through that. Other people have talked about, well, it's quantized in matter, not light. Okay, that's nice. The hard part was really how do you explain alpha helium diffraction, like Esterman and Stern, 1930. How do you explain that? That was really the hard part.
Uh, why would helium diffraction be a problem?
Because it's thought to be a particle.
Well, no, helium, yeah, bigger things than helium diffract. That's not even hard, and that's solid too. People say that, yeah, talk to people who work with neutrons. Everything they do is diffraction, reflection, and plus eventually it pops onto something. But
I know. They used the probability interpretation that it's a particle guided by a probability wave.
a
We
problem-
see the wave properties. You don't have to explain the wave properties. I know it does diffraction like that.
Well, the trouble with the probability wave is it does not account for the momentum effects of the package that you're looking at. You can have a directed probability wave, and it will leave momentum on whatever it hits. It will reflect off of it. It will leave a momentum impact. Otherwise, light sails wouldn't work. So and that's why I have a problem with the Copenhagen interpretation as an extremum example. It says particles and waves, and each is an infinite extrapolation of some reality that seems to be a little bit more complicated. So it's nice mathematically, but it tries to transform everything into a classical perspective, and which is what they wanted. They wanted classical waves, and they wanted classical particles, so they just stuck the two together.
That's right.
And your
That's right.
experiments are always interesting, Eric. The correlations are fascinating. I'm glad to hear some people are taking some interest in it. Um, uh, yeah, yeah. So interesting experiments, interesting correlation for that. I would make
You're-
a suggestion that you not use partially reflecting mirror as soon as you say mirror, everybody who hears you from quantum science is going to think you're talking about a very specific phenomenon when you're really talking about scattering. There's nothing wrong with saying scattering for what you're doing. You're saying you scatter it, you get this kind of result, and the result can't be explained. That's enough, But if you say partially reflecting mirror, that has a really specific meaning, and it is just like I did. And when I say but you can't do that with gamma because we can't build those things. So you're talking about something a little bit different. And
They do have reflections of gamma. There's a
you
gamma
have
ray
reflections,
spectrometer.
but coherent reflections, you have to be careful. Coherent reflections have very
It is coherent. It's a bent crystal of quartz where you could do a spectrometer of gamma rays and you could see the angles as a function of electron volts.
you can redirect a gamma
Yes.
ray with a
Yes,
bent
you can.
quartz
Yes.
crystal?
Yes. Yeah. There's a book by Semat that shows I could try to go grab it
Oh,
right
geez,
now.
no, I'll try to look that up. That's interesting. I never.
Yeah. There's a gamma
actually-
ray spectrometer that does show the coherence where you can diffract gamma rays. It was hard to do.
Ooh, I will look that up. I mean,
Oh,
I'm gladly stand corrected on that. Like I say, I
yeah.
know mostly from the X-ray domain. They're just the fits they had to go through to get X-ray reflections at very
Yeah.
low angles. I mean, you have these very elaborate, precise graphite.
It is a
color-
low angle with the distance between atoms.
Well, and a bent crystal makes sense. If there's some way you're going to do it, a bent crystal with a regular quantum frequency internally would make sense as a possibility for having an effect on gamma ray that could actually occur. I just never heard of that work. That's intriguing.
It's in a textbook by Semat, SEMAT.
SEMAT.
Yeah.
Oh, that's actually kind of, there's the Mossbauer. I mean, the Mossbauer is a gamma ray effect that deals with the entire rod as a quantum whole. So there's certainly interactions between gammas and large collections of atomic matter. Otherwise, you wouldn't have the Mossbauer effect. Nobody would have predicted the Mossbauer effect. That's one of those ones that just popped up and they said, oh, okay, well, here's how we'll explain it. But nobody would have predicted it because it just seems impossible for the gammas to interact that strongly with particular vibration modes of a metal object. So I'll look that up. SEMAT. That's intriguing.
I think I'm ready to call it quits by now.
I'm off. Thanks.
Let's see. Let me put my webcam on and sort of sign off and thank everybody. Thank you for the good feedback and the opportunity to present the experiment.
Yeah, thank you to you too. Yeah, this is fourth presentation that I've been attending from you.
Bye.
Bye-bye.
Thank
Bye.
you, Eric.
Bye.
Thank
Bye.
you.
Great presentation. Look forward to number 5.
Thanks, Eric.
That's great. She was in Berkeley.